Hello everyone.
Good morning, sir.
Good morning. Okay, I do you have any questions from the last class? And I want to clarify two things first. But anyway, before that, how many students are here? 24. Okay, I don't know how many class we have further. I don't know this Saturday is the working day or not. Yesterday was the Friday working day. Anyway, so do you have any class? Do you have any questions from the last class?
Sir,
Yeah.
this Saturday is not working day, but this Friday is a buffer day.
Buffer day. Okay, let me check. When is the last class?
Today is the last.
Today.
Today is the last teaching.
Today is the last class. Okay, okay. Let's talk about a little more. Okay, just general acid and general base catalysis. I want to finish. Okay. Actually, this time I taught. Okay, let me tell. So this time I taught very slowly compared to last couple of years. Okay, I'm teaching last 4 years. But anyway, slow teaching is not a bad thing. Okay, as long as you can understand. So okay, so let me start first. Okay, so two things I want to clarify. So last class there are two things was a little bit of debate. Okay, after that I thought about that what is going on. Okay, the first thing is that someone asked me about this reaction, that is a specific acid catalysis reaction, that is a ring opening reactions of epoxide, okay, using H plus specific acid. So someone told that, and I also argued that okay, we may get entropy of activation positive, negative, but regardless, we can see here in the rate determining step, two molecules are coming close to each other and involved in the rate determining step. So the del S will be always negative. I looked at the value for other type of reactions by substituents of the R, okay, and it's always negative. But okay, it is always negative. And so principle is correct, whatever we discussed. But the value will not be very much negative. So this is the table I showed you like 1 month before probably, that whenever we are teaching about the nature of the transition state and activation parameters. So you can see that when it is the SN2 type of reactions, okay, because this slide I'm showing because I have other values, but this slide I'm showing because this slide I already showed a couple of weeks before. So you can see when they are the free SN2, its value is about minus 30. Okay, but for the epoxides, okay, that's a good point. Whoever raised questions last time, you can see the value is minus 6. Still, it is minus. It will be minus, but it is not very negative value because the energy of the rate determining step and the not energy, the entropy differences between the ground state and the rate determining step or transition state in the rate determining step, it will be the gap will be not very high because the in the rate determining step, this carbon oxygen bond is breaking and it is ring opening, and starting material has a decreased entropy because of the ring strain. Okay, so you can see the value. If it is another SN2 type of reactions, you can see it is minus 31, but for specific acid catalyzed ring opening of epoxides, the value will be still negative, but value will be less compared to the SN2 reactions. Okay, is it clear? Is it clear or not? Hello. If it is not, I will go fast today. Okay. So next clarification is how the K ops is dependent on pH, right? Okay. After that, I don't know what happened. This experiment actually I did many times during my PhD. I thought what happened? Okay, it should be there. So after the class, I derived myself in a piece of paper, and I took a coffee, and I'm going to show that how K ops is dependent on KH. So this is the equations I showed you. Substrate and H plus is giving SH, and SH is giving to product. Okay. So dP divided by T, that is a rate, equal to rate constant, overall rate constant into substrate into the catalyst concentration. Okay. So the K ops is actually the combination of this part, these two part. Last time whatever confusion comes is because I told that it is the combinations of K and concentration of S. But It is not. So I'm going to tell you the detailed experiment because I did it many times myself in laboratory. So what experiment you will do to know whether it is a general acid or general base catalyst reactions. Okay. So again, I'm going to tell because this is my handwriting. So S plus H plus is giving HS plus, and then second step is the rate determining step to give the product. So that I showed in the last slide, right? So what is the rate? Rate equal to K2 SH plus. If you have any doubt, just let me know. Okay, raise the questions. Okay, please ask me. Equal to, so this is the K1 divided by K inverse 1 into concentration of substrate into concentration of catalyst. So this is the catalyst H plus, right? So K ops equal to K ops into substrate concentration. So K ops is actually K into catalyst concentration. So in experiment, what you will do, you have to, doesn't matter, you can use titrations, you can do spectroscopy, only you need to determine what is the concentration of product or what is the concentration of starting material with respect to time, right? That is the kinetics. So first you have to determine the rate law, right? So what we will do, suppose this is the first order, right? It is the first order. In specific acid catalyst, this is the first order. So if it is the first order, so what plot you will do? ln substrate versus time. If you plot, it will be a negative slope, right? Because substrate concentration is decreasing. Or you can plot in the opposite way, substrate concentration ln product versus time, slope will be positive. Is it clear? So now you can see the slope. If you increase the catalyst concentration from here to here, means you are decreasing the pH. On increasing the catalyst concentration, that is H plus, or decreasing the pH, your slope will be higher, right? Because this is first order with respect to the catalyst H plus. Here catalyst is the H plus. So you will get a different slope. So slope will be higher if you increase the concentration of catalyst, that is H plus, or decrease the pH. Is it clear?
Yes, sir.
Yes, sir.
Is it clear, right? Yeah, I did it myself. Okay, I don't know what happened last time. I confused. Okay, this is the problem of online teaching. If I bold, then my hand is like, okay, it's just like a practice hand. Okay, but many times. But anyway, so now what is the slope? Slope is the, what is the slope? Slope is the K ops. Okay, because you are determining, you can see you are determining the concentration of product or starting material with respect to the time. Okay. So this is the K ops. So what will be the slope? Slope is the K ops. So what is the K ops? K ops is K into catalyst concentration. So if you plot K ops versus increasing catalyst concentration, then you will get a straight line. You will get only straight line if it is a first order. If it is not a straight line, if it is no slope, flat line, means it is zero order. This is the way you can determine the what is the order of the catalyst. If it is a straight line, then this is the first order. If we just convert the pH plus into pH, then it is just the opposite. Okay, you will get the negative trend. K ops versus pH, it will be the negative slope if it is a specific acid catalyzed reaction. Is it clear? I hope my handwriting is not great, but at least is it okay in slide?
Yes, sir.
So this is the experiment you need to do. This is the very simple experiment. What you need to do, only you need to change, you need to check what is the concentration of substrate with respect to time, either by titration or by NMR, or you can take other techniques also, say many times IR also, if you have a specific peaks. Okay, so changes of substrate concentration or changes of product concentration with respect to time. Once you get the plot, then rest is nothing, only the Excel or graph paper and calculator. Okay, so now I hope it is clear. So I told you, so okay, so if K ops in specific acid catalyzed reactions, so K ops, it is depending on the pH or log K ops. Okay, if it is the negative slope or increasing the pH, if it is a decreasing, that means it is specific acid catalyzed reactions. And in a buffer solution, a pH is the same, but you are increasing the slightly of the weak acid, which will not change the pH. And if you see all the plots here, suppose you have 5 data points here and K ops is remain same, that indicates that this is not a specific acid catalyzed reaction. Okay, because it is solely dependent on the concentration of H plus or pH. All right. Okay, so what about general acid catalyzed reaction? So general acid catalyzed reactions, these also, you know, I am just telling you again. I am going to tell you with a examples. Although it is a last class, or maybe we can take one more extra class, that we will decide. Okay, so this is, I'm going to tell you with examples and how to study the rate determining step based on the 4 experiments that I told you: rate law, activation parameters, Kh by Kd, and Hammett plots. Okay. So this is an example of general acid catalyzed hydrolysis. This is the acetal hydrolysis. This acetal is the derivative of cycloheptatrienone. It's a ketone, and then if you just protect the ketone with ethoxide in ethanol, you will get the acetal. Okay. So in the hydrolysis, this acetal is converting to the corresponding ketone. All right. So here, how the hydrolysis is going on in presence of acetic acid, that is the catalyst. That is the catalyst in water medium. Definitely, you have water. You have water. Water is a solvent. Okay, so this is the mechanism. I'm just telling the example. I'm going to tell you the what is the mechanism. Okay, so then I'm going backward. That what kind of experiment will support this to make you more understandable about these 4 experiments, whatever I taught in last 1.5 month or maybe more. So this is the mechanism. You can see that ethoxide, this is the arrow you can see here. The first one ethoxy CO bond will break. Here it is attacking here, and acetic acid OH bond will break. Okay, to gives this intermediate. So this is the rate determining step. So if this is the rate determining step, then what will be the rate law? This is a unimolecular or bimolecular reaction?
Bimolecular reaction.
Bimolecular reactions, right? So rate law will be the first order with respect to this starting metal as well as the catalyst. That is the general acid catalyst. That is the acetic acid. ACOH, acetic acid. I know what is acetic acid. CH3COOH. Right? All right. Acetic acid. You can see here, interestingly, that if you deuterate the acetic acid, those are commercially available, then you will get a rate constant. Okay. Oh. You will get a isotope effect Kh by Kd, K acetic acid, protic acid versus acetic acid deuterated. Those are commercially available, or you can also make it yourselves. That is very easy. Take the acetic acid and add deuter and then distill. Okay, so there will be proton exchange. If you do that, since OH bond is breaking, not here, it is not CH or CD. Doesn't matter. The concept is same. Here is OH or OD. Okay. It is OH or OD bond is breaking, so you will see a primary kinetic isotope effect. Okay, and here you can see the value is 1.5. Does it make sense? Interesting. That yes, indicates that definitely for the catalyst, this is the general acid. Here OH or OD is breaking in the rate determining step. What should you expect for entropy of activation? Positive or negative?
So negative.
Negative. This is actually negative. This is negative. In general acid catalysis, always you will see a negative del S compared to specific acid. I told you that specific acid catalysis del S entropy of activation, changes of entropy of activation may not be meaningful. It all depends on what is the mechanism. It is the unimolecular or bimolecular. I showed you with examples. Okay, I'm not going to tell any derivation. Okay, showed you in examples. But in general acid catalysis, always you will see a primary kinetic isotope effect that you should expect. Those are the experiments you need to do. Okay, not only for that, you should expect the del S of activation. Okay, is always a negative, huge negative value. Okay, this is a okay. We have more. How it is pH dependent, that I'm also coming next. Okay, so this is another one example of general acid catalyzed hydrolysis of orthoester. Okay, so acetal or orthoesters. Here general acid is also acetic acid. the first step is the rate determining step, where OH of the acetic acid is being broken in the rate determining step. Okay, arrows are quite clear, right? To give this derivative of ester product, okay, then you can see here, then the isomerizations will take place. Okay, then remaining you just follow it by the reactions of water. Okay, there are multiple steps. You can see there are 2 arrows or 3 arrows. Okay, there are this means there are not like that only one intermediate. There are multiple steps. You draw yourselves. I'm not going to draw. Okay, this was very simple. After that, water will attack here. Okay, then this is simple hydrolysis to give the acetic acid and methanol. Okay, so here what kind of experiment you will do? First of all, you will do the Reid law. On Reid law, you should see this is a bimolecular. Not only for that, KH by KD, you should expect a primary kinetic acid effect. Entropy of activation, you should get negative. Not only for that, then next I am going to tell you that how the K-ops is dependent on pH. That is the last another one experiment, right? There's a pH dependence of K-ops versus pH. What will be the nature of the plot? That is the additional experiment. You can also do that to understand or find which step is the rate determining step. Okay, so for that, this is the equations. There are a lot of some sentences are there. I'm going to read it, so you do that. So here the substrate and general acid, not H plus specific acid. This is an equilibrium. The similar type of equations for specific catalyst reactions. It will give the SH plus plus A minus, and then this will give the product. Okay, so your rate equal to K into concentration of substrate as well as weak acid. So it's the same thing. Whatever I showed you in my handwritten slides before that. So if you do that, K-ops versus concentration of weak acid, that is the catalyst. Then on increasing the catalyst concentration, this is the catalyst concentrations, you should see, unlike specific acid catalyst at a constant pH, you should see that your K-ops is increasing on increasing the concentration of weak acid or catalyst. Okay, and what about the pH? It's a reverse way. pH will drop, but it will be remain constant when pH equal. There is Henderson equations, right? When the base is more than acid, okay, pH equal to pK what is that, plus log of A minus divided by HA. Okay, so main thing is that you need to do that K-ops versus HA concentration, catalyst concentrations. Okay, if you see this is the first order with respect to the catalyst, that is the weak acid, then it will support this mechanism. But not only for that, you have to do another 3 experiment to completely understand what is the rate determining step. Okay, so one is the isotope effect. Another one is that Reid law. Not Reid law is always the first things, because you need the Reid law for everyone. Rate constant K, here is the K, here is the K. You also need the K here. Okay, so always you need to do the first experiment you will do is the Reid law. Then the rest of the things, even the isotope effect from Eyring equations. Okay, ln K by T versus 1 by T, that plot, you need always the rate constant. So Reid law, determinations of the Reid law is the first experiment. All right. So just I want to heads up for the specific acid catalyst versus general acid catalysis. I told yesterday that H plus, the specific acid catalyst reactions, it is very specific, only specific about the H plus, not very specific. It is a specific to only H plus or H3O plus. Okay, but in general acid catalysis, normally any catalyst, but it can be weak as catalyst, it can be strong catalyst. Okay, it all depends. Okay, about the mechanism, but normally it depends on the what is the acid. So in one of the distinct feature for general acid catalysis, I told you that proton transfer involved in the rate determining step. That is the reason why you will get the primary kinetic isotope effect. It may be CH or CD or OH or OD. Okay, but here in specific acid catalysis, you should not see any primary kinetic isotope effect. Another important thing is that The Del S value, it can be positive or negative. Okay, it depends on the type of the reactions, what is the mechanism. But for general acid catalysis, you should see a large entropy of activation. This is the difference. So by determinations of the Red law, okay, for another one is the Red law, right? So Red law, the determinations of the activation parameters kH by Kd as well as Khouse versus pH or concentration of acid. Okay, so you can easily distinguish a reactions, acid catalyzed reaction. This is a specific acid catalyzed reactions or general acid catalyzed reaction. All right. Any questions? Quick. Otherwise, I will go last. I think we have to move forward. Then I am here for another half an hour or 1 hour to ask your questions. So, but these stuff is quite easy, right? Because you already know from Professor Saswant's lectures. Okay, I'm just giving you the examples because those are all related to the four experiments, or now maybe the Khouse versus pH plot. That is another one experiment. Okay, related experiment. Okay, the 5 experiments that will be helpful to understand the nature of the transition state in the rate determining step. Okay, so next is the specific base catalyst reaction. So you know that is a specific base. So if specific acid H plus, then specific base is OH minus. Okay. So in specific base catalyst reactions, the base is always in equilibrium with a substrate, which generates a base or nucleophile. Okay. Actually, this is called nucleophile, not base. Okay, I will come up what is the difference between base and nucleophile. So it will generate a nucleophile which is more nucleophilic compared to the previous one, and then it attack on the another one substrate to give the product. So this is a base specific base catalyzed ring opening reaction of epoxide. So previous one was the specific acid where H plus bind here on the oxygen, right, in the oxygen here, but here this is a specific base. So what base is doing, that OH minus, it is actually deprotonating the methanol to give the methoxide, which is more nucleophilic compared to the methanol, and because of the high nucleosity, it is attacking to the carbon center adjacent to the carbonyl oxygen bond, and the ring opening is taking place. Okay. Just 1 second. Okay, if you have any questions, just ask me. Just I need a few second break. Just. Okay. So for the experiments, so in specific base catalyzed reaction, so what will be the entropy of what will be the Red law? What should you expect? Red law?
Second order.
You should expect the second order. Okay. All right. Just hold on, just one urgent call. Oh, sorry. Actually, I had an urgent call from my lab. So. Okay. So here, if you plot the K-ops, okay. So K-ops will be also the same thing, that K into concentrations of OH minus, okay, the base versus pH. Then you should expect that if it is a specific base catalyzed reactions, then on increasing the pH means that is the increasing the OH concentration of OH minus, you should see a positive slope. That's just opposite of the specific acid catalyzed reaction, right? In specific acid catalyzed reaction, you should see a negative slope, but it's just the opposite one. And not only for that, if you use a buffer solutions, right? And the same thing. So in buffer, pH will be remain same, but if you just increase the concentration of base small amount, so that the buffer will prevent the changes of pH, so pH is same, then you should expect that K-ops is remain same unchanged. Okay, because it is also solely dependent on the concentration of OH minus or pH. Okay. Okay, so next is the general base. Okay, the very short. Okay, so because you know that. So now actually I'm going to tell again for general base catalyzed reactions with examples, and then how can you use these 4 or 5 experiments to distinguish between the specific base catalyzed reactions and general base catalyzed reactions. Okay, so this is a example that is widely used by organic chemists. That is the conversion of alcohol to ester or protection of alcohol using acetic anhydride. So this is acetic anhydride. Acetic anhydride you cannot buy from market. It is banned. Do you know why?
Because it can be used in the production of I think alcohol.
Alcohol.
Or no. I think explosives.
Explosives. Any reason? Acetic anhydride is banned in the market. Without license, you cannot buy. Okay, this is out of topic. Okay, just cute. Okay, maybe 1 minute. Why? Any idea? Acetic acid you cannot buy. You need license.
It's corrosive. I mean.
Or corrosive. There are many chemicals. H2SO4 is corrosive, but you can buy. Any specific reason? Any?
Sir, explosive only. I think.
Explosive. There are many. Oh, there are a lot of gunpowder, bhaji, right? And those are in Diwali. Those are not explosive. Supreme Court is banned because of this. In Delhi, who are in hostels or it doesn't matter where are you in India, right? In Diwali last week, so many explosives has been burned. So, any other reason? Okay, so let me tell you. Otherwise, it will just only take the time. Acetic anhydride is used to make heroin. Have you anyone taken heroin? Do you know what is heroin? Have you heard that?
It is a drug that is given like.
Oh, that's enough. It is a drug, right? It is one of the most dangerous addicted drug. So how do you heroin is made? Most of the heroin is, what is the maximum product? Which countries produces the most amount of heroin? Which country? Afghanistan. Okay, so heroin is produced by simply acetylation. This is acetylations of morphine, and morphine is coming from the morphine flower. That is the morphine, right? This alkaloid. Okay, from poppy seeds, poppy plant. Okay, the flower. Okay, so it is simple acetylation. So this is the morphine. Okay, morphine has alcohol groups. It is converting to the acetals. It's the same reaction. Okay, but because of these dangerous reactions, this is a drug, one of the most dangerous drugs. To prevent it, you need license. Okay, only you can use it for research purposes or for any other specific purposes. You cannot get it from the market itself. Okay, clear? All right, so this is the reactions to conversion the morphine to the heroin. Okay, don't do that in home anyway. So okay, so here what is the reaction? So reaction is very simple. You have the alcohol. It is here alcohol. It will attack to the carbonyl carbon of acetyl acetonate. Okay, sorry, acetyl acetic anhydride. This is anhydride, not acetonate. Anhydride. Okay, and this is the rate determining step to give this intermediate, and rest of the things is the you draw yourselves what are the remaining steps, okay, to give this product. It's very simple organic reactions. Okay, so this reaction is quite slow, but if you add some base, okay, suppose acetate, so here also you can get the product. Okay, there is a product is acetic acid. Okay, if you add some base that acts as a general base, okay, general base catalyst, that is the suppose acetate, sodium acetate, sodium acetate. Okay, this is a general base, then it accelerates the reaction. Not only for it accelerate the reactions, it is regenerated. It is regenerated. Okay, this is regenerated because this is a catalyst. So what general base does? General base is also does a similar thing, that general base also deprotonate the alcohols and gives a stronger nucleophile, which helps to attack more quicker to the carbonyl carbon of the acetic anhydride. Okay, so this is the nucleophile, this is the electrophile, and this is the base. So this is another different kind of mechanism. So here you can see this is a concerted process. The general base is attacking to the nucleophile, and the simultaneously OH bond is being broken, and the generated nucleophile is attacking to the carbon carbon. So this is another type of possible mechanism. It can be specific acid, specific base, it can be general base. In specific base, what we will do, there will be an equilibrium with OH, right? There will be an equilibrium with this. But here, this is a concerted process. Two kind of mechanism is possible. So you need to find by experimentally that which mechanism is correct, is more favorable for this. Okay, so first things, you will do the order of the reaction. So what kind of order you should expect if this is the mechanism? If this is the mechanism in the rate determining step, then what kind of order you should expect? Let me clear again. Tell me, what will be the order? Suppose you draw, this is another kind of mechanism is possible. Mechanism rate determining step. So what will be the order? What should you expect?
So third order.
Third order, it should be molecular. Right, it will be the first order with respect to acetyl acetic anhydride. It will be the first order with respect to the alcohol, and it will be the first order with respect to the catalyst. Unlike the specific base catalyst reactions. Okay, so specific general base catalyst reactions, it will be the third order. Am I correct? You can distinguish from the order of the reaction. What else? What else? If you replace this alcohol H with D, you should expect KH by KD, primary kinetic acid effect, right? Am I correct? Yes or no?
So why?
Why not?
So because it is a concerted process,
Yeah,
right? It
yeah.
won't matter if it is H or D. In the
Yeah,
end,
OH or OD bond is being broken in the rate determining step.
that's okay, but it is not contributing to the reaction in the rate determining step, right?
This
Because
is the rate determining step. This is the rate determining step.
alkoxide is attacking the carbonyl carbon, right?
Which one?
So RO
No,
minus.
but this is a concerted process. This is happening together. This is a concerted process. That's why you are getting the tar molecular reactions. Order will be the first order with respect to this, and this. Arrow, forget about arrows. Okay, you don't know the arrows. Arrows I am drawing. Okay, but experiment is experiment. We are giving the arrows based on the experiments. So first of all, order should be 1, 1, 1. So total order will be 3. What will be the Ka KH or KD, that will be the, if you replace this OH or OD. OH or OD bond is being broken or not?
Yes, sir.
Yes.
It is broken. There should not be any confuse here. OH or OD bond is being broken here, right? You can see this is attacking here. And this is broken. Okay, I forgot about arrows. Regardless, this is being broken. So OH or OD, you should get primary kinetic isotope effect. Am I correct? Not only for that, what about the entropy of activation?
So negative.
Big negative. 3 molecules are coming close to each other: catalyst, nucleophile, and electrophile. Okay, that's enough. Not only for that, you should also expect that.
Sir.
Yeah, tell me.
So we won't expect RO minus species in the solution, right?
Which one?
RO minus species in the solution, in the reacting mixture.
R O minus.
Yes,
RO
sir.
minus.
Because
No, it is no RO minus. No, if it is RO minus, then that will be the, if it is the RO minus, then that will be similar to like a specific acid catalyst reactions. It's a concentrated, it's a concentrated process. Together is happening. If it is RO minus, if it is, okay, let me clear again. If it is, that's why I'm telling that what is the mechanism. There are 2 kinds of mechanism is possible. One will be that this is the first thing, right? Then generate the RO minus, then RO minus attack. Another process, another step will be, another mechanism might be the concerted process. We don't know. We have to determine the order of the reactions. If it is the whatever you are telling that RO minus will generate in the circle here, okay, then what will be the red law? Red law should be theoretically only the first order with respect to the electrophile, because those are the reversible steps. If it is not the rate determining step, if this is the rate determining step, okay, then it cannot be tri-order reaction. Is it fine? Clear? This cannot be tri-order reaction. Theoretically, it should be only the electrophile reactions. It cannot be tri-order.
Sir.
Yeah.
If we had NaOH, for example, instead of
Okay.
this acetate catalyst,
Yeah.
so RO minus would have been formed alkoxide basically.
Exactly. It may
by
happen.
equilibrium.
Yeah. Then that will be
Then it
converted
would-
to the specific acid, specific base catalyst reaction.
Okay.
Okay.
Yes.
Or I'm going to tell you, or I can also tell that suppose you are using NaOH, although NaOH is a very strong base, suppose your pH is not very high. So OH concentration is very low. Okay. It may also go to the tri-molecular reactions in a different pH. It may go. I don't know unless you do the experiment. I want the experiment first. That is the reason in the quiz I asked you what is the mechanism. Mechanism is that pathway that disproves all other pathway. You have to do the experiment too. You have multiple pathways possible. I can take a pen and paper, and I can tell this is a concerted pathway. Someone is telling it might be this circle is the first pathway, right? Where the generation of the alkoxide, it can be one pathway. So I can see there are 2 kinds of pathways. How can you distinguish one from each other? Order can tell. KH by KD can tell. Definitely entropy of activations will be hugely negative, no doubt. But still, if it is it may be negative, it may be positive, but it may be negative for both cases. Definitely here order can be very distinguished, tri-order versus mono-order or di-order. Not only for that, K-house versus base concentrations will definitely tell this is the specific acid catalyst reactions or base catalyst reactions. Okay, definitely. Okay, so just to heads up that in specific acid catalyzed reactions you have to do the experiments, so it is very specific to OH. Here tail S, I told you it can be, most cases it is negative, okay, but if it is the genyl acid, because it is a tri-order, it will be hugely negative. Order can be distinguished. Not only for that, KH by KD, it can also distinguished to each other, because here the OH or OD bond, it is alcohol, that's a OH or OD bond. Maybe other reactions also there, okay, where CH or CD bond may also breaks, okay, that is possible, okay, but regardless, where it all depends on where you are substituting D with H with D. So here the proton transfer will involve in the rate determining step, so you should expect the primary kinetic isotope effect, unlike specific base catalyst reaction. Okay, so those kind of experiments you can do that. So here entropy is confusing for both cases. Be careful. In the specific specific base, entropy can be negative, but you should expect a very large negative always for the general base, because 3 molecules are coming close to each other. Okay, so there will be huge negative value of del S. Okay, from the value also you can distinguish. Okay, if you know that, okay, this is my 2 options or 3 options, so how what kind of value you should expect, that also you can do that. Okay, okay, I think I should go next. If you have any questions, please ask me after 10 minutes. Okay, okay, should we take a class tomorrow? Tomorrow is a buffer day, right? Hello. Hello.
Yes, sir. Yes, sir.
Yes, sir.
Are we available?
Yes, sir.
So at which time? Maybe half an hour class. I just want to finish another one class of lecture. Okay, another class of catalyst. That class people got Nobel Prize this year only. So I think we should learn what is that. Right? Why not we should learn about the content of the Nobel Prize of Chemistry in 2021. Okay. So David Macmillan from Princeton and another person from Max Planck. There are a lot of Max Planck. That is Max Planck Berlin, I guess. His name is I'm forgetting his name. He has a lot of Indian student. So 2 people got Nobel Prize for discovering of nucleophilic catalyst. Okay, it is not like that I included the slide because people got Nobel Prize this year. Okay, I'm teaching this nucleophilic catalyst every year. Okay, it's already in the syllabus or content of our lecture. Okay, but fortunately this year people got Nobel Prize. Okay, I think let's start it. Okay, then tomorrow within half an hour we will finish, and whatever the questions you have, I will also upload the slide today. Okay, in Moodle, and we will discuss tomorrow. So tomorrow at 11 o'clock, let's have a half an hour class. Okay, 11. Okay, so next is the nucleophilic catalyst. So see, so there are a lot of catalysts there. So okay, engineering people, if you go to do any project in chemical engineering, IIT Delhi, majority, I think 90% people are working on experimental on catalysis, or some people also does theoretical calculations on the catalyst. Okay, I think all, whatever I know, the people in the chemical engineering. So catalyst, okay, you know from your high school that catalyst can be 2 classes. It can be divided into 2 classes. That's true. One is homogeneous catalyst and another one is heterogeneous catalyst. But homogeneous and heterogeneous, those are the phase wise. Okay, the phase that, okay, homogeneous means it is the same phase with solutions, and heterogeneous means the reactant or solutions and the catalyst are in the different phase. Maybe solid gas, liquid gas. Okay, not like gas or solutions or solid. Okay, those are homogeneous. Okay, so but if you look at in the terms of nature of the catalyst, then we can divide the catalyst in couple of parts. One is the metal catalyst. You know that metal catalyst like Wilkinson catalyst, right? That is based on the rhodium metal. Another one is acid and base catalyst that we have learned, right? General acid, general base, right? General acid, general base, H plus, Y minus, or any kind of acetate, the general base. Okay, so those are the other class of catalysis, that is the acid or base catalysis. The third type of catalysis is nucleophilic catalysis, and why people got Nobel Prize this year, because this is a new generations or new type of catalysis they invented recently, I think last 15 years before. Okay, I think first paper came in probably 2000, so maybe 2000 or I forgot which year. Probably like 15 years before. It's not very new. Metal catalyst, acid catalyst, base catalyst, those are known for centuries. Okay, but nucleophilic catalyst, although it is known in nature, but they first revealed about the nucleophilic catalyst and how to use it for various kind of reactions, and because of that Nobel Prize was given in this field. Okay, so what is nucleophilic catalyst? You can see catalyst should be nucleophilic. Okay, or catalyst can be nucleophile. Okay, those are also called organocatalyst. Okay, organic molecule itself acts as the catalyst. All right. So the catalysts are. So what is nucleophilic catalyst? Nucleophilic catalysts are a organic molecule, not metal. Okay, it's an organic molecule which acts as a nucleophile. Okay, which can also act as a Lewis base or nucleophile. I'm coming, which involves a Lewis adduct as a reacted intermediate and activate the molecule. Okay, not only for that, you know the catalyst. One of the nature of the catalyst is it have to leave at the end, so it have to be regenerated, right? To make a cycle, right? To turn over, the catalyst need to be regenerated in a certain point of a catalytic cycle. Okay, so catalyst, it should attack on the substrate as usual, and it should be a good living groups to complete the cycle and for the next turnover, right? So catalyst will attack to the substrate, activate and leave. So catalyst will come and then will leave, right? To complete the circle and turn over, right? Turn over, repeating. Catalyst means is repeating, right? How many turnover, how many repeating in the cycle, right? That is a catalyst. So I want to make sure one concept is clear. Okay, there is a difference in between base and nucleophile. They are not same. Do you know what is that? Any from CML 100 or high school? If it is not, let me tell you. Okay.
Sir, if it is given to hydrogen, then it's base, otherwise it's nucleophile. Electrons are given to hydrogen, then it's base, otherwise to
But
if
same
it
thing
is
can also give the both then.
Sir, a base is characterized by the equilibrium.
Okay.
Its strength is
Good.
characterized by equilibrium, but
Yeah,
a
yes.
nucleophile is basically a one. I mean, it goes in one direction only.
Which one? Nucleophile.
Nucleophile.
Okay, that's a good thing. Okay, it's not like that. Okay, we have shown the equilibrium, but it's true that base is okay. So someone actually, whatever you are telling that is correct, but there is multiple criteria. So normally the base, suppose let's talk about the Lewis base. Okay, Bronsted base is a OH minus, but okay, that is fine. But let's talk about the Lewis base. Okay, the nucleophilic is closely related to the Lewis base. That will donate electron. Someone told, right? Donate electron to something. So one of the common thing is that base reacts with acid, means that is donate electron with H plus, right? And give the salt or salt. Okay. So if this is the case, those are called base, and normally they are in equilibrium. But if the same molecule or different type, similar type of molecule, if they attack to a carbon center, so I don't know, you know hard-soft principle or not? Hard-soft principle. So H plus is hard, okay, but carbon center is soft. So if the same species or similar species, they donate electrons or attack to a carbon center, in more general, those are called nucleophile. Okay, why nucleophile? What is nucleophile? Nucleophile means, you see the English, file means, what is file? File means
donation. Giving.
Loving, like
love, yeah, love, right? File, not donation. No, it is a wrong thing. I'm talking about the English. File means philic. File means love. Hello. Anything? Any ask questions? Okay. All right. So yeah. So nucleophile. What is the charge of nucleo?
So nucleus positive.
Positive charge. Nucleophile means it is the positive charge lover. Very simple things. Okay, don't get confused. Okay, nucleophile means it is the positive charge lover. Okay, so if I am a nucleophile and I love positive charge, definitely I will be either electron rich. I have the, even I am the neutral, I should have the electron pair, right? So that I will attack on a positive nuclei, or I can be negatively charged. Okay. So the common sense I'm coming next, okay, and I will give in the more details about the difference between the base and nucleophile. Okay, in the common sense, if any Lewis base, which it can have lone pair or it can be negatively charged, definitely it has lone pair. If it is attack on the carbon center, then those are called nucleophile. Okay, and if it is very specific, it is on when it is attacking H plus, reacting with H plus, those are called base. All right. Okay, reversible. Okay, this is a like a more features about the distinct feature about the base and nucleophile. I'm going to tell now. Okay, so I will finish today with this is the last thing. So nucleophile, I told you. So nucleophile, it attack to the carbon center. So make sure whatever the Lewis base, it need to be attacked to the carbon center, and those are called nucleophile. Catalysts need to be regenerated. Okay, so if any nucleophile, it is activating a substrate and then it is leaving later, those will act as a nucleophilic catalyst. And most of the cases, nucleophilic catalysts are this kind of catalyst. Like you can see the pyridine. Okay, it is called, this is a pyridine moiety. So pyridine, you have lone pair here. Okay, these are the Lewis base. Okay, it is attacking carbon centers. So you can see mostly pyridine or pyridine derivatives or imidazole or N-methyl imidazole, NMI. Those are very common. Or another one is the DABCO. Okay, DABCO. Okay, you can see this is a tertiary amine, DABCO. Okay, tertiary amine, tertiary, all acts as a nucleophilic catalyst, commonly used in many organic catalytic reactions. Okay, very common, they have a lot of applications, orthoacylations, orthosilylations, Bailey-Zillman reactions. Maybe tomorrow I will discuss. Okay, one of the interesting feature, not interesting, this is the important feature of nucleophilic catalyst is that they are highly sensitive to the steric. Why? Because this is attacking to a carbon center, right? Carbon is already, I would say it is quite steric. It's not like H plus. It is, carbon is already substituted or bonded with 4 atoms. So carbon center is quite steric. So nucleophilic cannot be steric. If you have any steric crowding, suppose you have a methyl groups like here, you have a 2 methyl groups, that is lutidine. Okay, so those cases it cannot attack to the carbon center. It cannot, because of the steric. They prefer to attack H plus. That is the reason these molecules, especially lutidine, choline, they are called proton scavenger. What is scavenger? What is scavenger? English.
It feeds on something. Scavenger is basically an species of animals. Oh, birds. Sorry.
What is scavenger?
Sir, picking up something left over.
Yeah, crow is a scavenger, right? I know, we know from your primary school, right? Scavenger means picking whatever you got it. Okay, you have a small piece of dirty foods are there, they will scavenge. Okay, and they will clear it off. Okay, similar like this. That's why this is a term. Okay, interesting terms in chemistry. Proton scavenger. What does it mean? They are, if you have any proton left in the solutions, they will always absorb this proton, and they are very specific to the proton. So always they will react with H plus only. H plus only. Okay, if you have other kind of protons or you have the other kind of reactive carbon centers, it will not attack. It will only attack on the H plus. So those are act as a base. Okay, only base, not nucleophile, and they will attack only H plus, because if it is the greater than, if any size is greater than H plus, it will cannot attack. Why? Because of the sterics adjacent to the nitrogen atom or nitrogen donor. That's why those are called proton scavengers. Okay, I think I will go remaining part. Okay, tomorrow. So tomorrow at 11 o'clock. Okay, for let's do it half an hour, and after that, if you have any questions, we'll discuss. Okay, if you have any questions, you can ask me also today. I'm here. Questions? Okay, I think you people should be. I don't know. It all depends on you. Okay, you want more content this time. This year I didn't teach much. I was teaching very slowly. Maybe most of the people are happy so that your syllabus is less. But some people I know that you want to read or learn more. I'm sorry for that. Okay, so anyway, you have a lot of stuff to learn in your whole life. So one class is not enough. All right.
Excuse me, sir.
Yeah, tell me.
Sir, tomorrow, if you're holding a class, could you tell us what time? 10 or 11?
11. Is it okay?
sir. Yes,
Same,
sir.
11. Let's do that 11. Tomorrow is the Friday. Let's do it 11. Okay.
Okay, sir. Thank you,
Yeah,
sir.
and in Moodle I will upload today afternoon. Okay. Yeah. Anything else?
Thank you, sir.
Please no. Then thank you. See you tomorrow. Okay. Read it, and if you have any questions, please discuss with me tomorrow. Okay.
Thank you,
Bye.
sir.
Today also I am available. So otherwise I will leave if you don't have any questions. Okay. Then thank you. See you tomorrow.